The reason it's wrong is because we've only really considered this side of this kind of conceptual model. We haven't really considered this side over here. Okay, so this is where the greenhouse effect comes in. Okay, so what's happening here is the Earth heats up. Okay, the Earth, because it has some temperature, it means it's radiating its heat out to space, but that doesn't go straight out into space, that energy. Okay, some of it gets intercepted by the atmosphere. Okay, that causes the atmosphere to heat up. Okay, so the atmosphere then has a temperature, so then the atmosphere is also then radiating heat away. Okay, and it radiates heat up out into space, and it heats radiation down to the Earth. Okay, so we can. Well, that's the go. Okay, so we can start to look at about why that might be. So so this is a graph that's got. Look at it. So we've got wavelength across the bottom. So this is very short wavelength. So this is kind of ultraviolet light. Okay, moving into infrared. Okay, and we go moving off the other side into kind of like radio and microwave kind of radiation. And because the sun is very hot, okay, it radiates energy in the visible spectrum over here. Okay, but the Earth is not so hot. Okay, so it emits in the infrared spectrum over here. And it turns out that the atmosphere is actually quite transparent in the visible spectrum and is actually quite opaque, so light can't really shine through it in this infrared region. And that's because the atmosphere is made up of all these different kind of gases and molecules, and those molecules can absorb different frequencies of radiation. Okay, and the reason for that is that, say for instance, a carbon dioxide molecule, that's a carbon atom with two oxygens on the end of it. A water is an oxygen with two hydrogens on the end of it, and those bonds between the oxygen and the carbon, and between the oxygen and the hydrogen, they can stretch and bend. Okay, and that stretching and bending is what the mechanism by which those molecules absorb radiation. So a bit of radiation comes in, and if that radiation is the same frequency as the natural frequency of that bond vibration, it will excite those bonds and vibrate them a bit more. It's how microwaves work. Okay, so microwaves send in electromagnetic radiation that is the frequency of one of the bond vibrations in water. Okay, that means that it causes water to vibrate more, and all of the microwave energy is absorbed by that molecule. And the same thing happens in the atmosphere. Okay, and it turns out that there aren't many molecules that have this high frequency vibrations. Okay, so the short wavelength light doesn't get absorbed, whereas these longer wavelengths do get absorbed. Okay, so we're going to build up this really simple model now. So I've simplified that cartoon of the climate system right down to something very, very simple. So we've got space at the top, we've got a layer of atmosphere, which is just one layer. So the atmosphere is not just one layer, it's many layers, and we've got the surface of the Earth. Okay? And this is the kind of thing we want to know. We want to know the temperature of the surface of the Earth, because that's a thing we can kind of relate to, that's the thing we can measure. So we've already described this part of the model, okay, where the incoming radiation, so the solar flux divided by 4, because we're living on a spherical planet, that comes in, and then some of that is reflected, so in our case 0.3 of that that's coming in is reflected out into space. Okay? So we've done that. Okay, and that can be described, there's the maths for that. Okay? Now we've got this, that causes the Earth to heat up. Okay? That gives it a temperature, and that means that it will be radiating kind of this long wave radiation back out, up into the atmosphere, into the space. Okay? Ooh, sorry, lost my Twinkie. Right. So when this hits the atmosphere, some of that energy is absorbed. Okay? And some of it goes back out, carries on going up through the atmosphere. So we've got this term absorptivity. Okay, so all this is the fraction of this radiation that is absorbed by the atmosphere. Okay. If you remember back to the video, we had this term called black body. Okay, so if the atmosphere was a perfect black body, it would absorb all of the radiation that is emitted to it, okay? And the emissivity, or so the absorptivity would be 1, okay? So it would absorb all of this and nothing would get out into space, okay? Okay, so that means that there must be some energy being absorbed by the atmosphere, okay? And that causes the atmosphere to heat up. Now, and that causes the atmosphere to then radiate heat up and down, okay? Because just imagine it's just like a slab of metal, okay? That would be radiating heat down and up, okay? Because this is the energy emitted per surface area. The surface area down is the same as the surface area up. Now, it turns out that we also have this term of the absorptivity, or in this case, emissivity, okay, in this term, which because the atmosphere is not this perfect black body, okay, it doesn't quite obey that kind of Weems law, Stefan-Boltzmann constant relationship, okay? So even though it has a certain temperature, it doesn't quite emit the amount of radiation that it would do if it was a black body, if it was like a perfect thermodynamic object. Okay, it only emits a fraction of that, okay? And the reason is because the energy gets lost through interactions with some of the molecules, because the gas, they start moving around, the chemical reactions happen, all sorts of stuff, weird stuff happens. But basically, this number, so the fraction of which of a perfect black body which the atmosphere emits, is very, very close to the fraction of the black body that it absorbs. Okay, so we can use this absorptivity term when we're describing how much the atmosphere absorbs, and this emissivity term for the fraction of the theoretical maximum which it emits. Okay? So what we've got now is we've got a slightly more complex model that incorporates these fluxes into and out of the atmosphere, as well as the shortwave radiation that basically doesn't really interact with the atmosphere, that just comes in and bounces straight back out, or interacts with the Earth. Okay? So what we can do, okay, so we basically now can describe all of these fluxes, except maybe some of these smaller ones, these latent heat fluxes and stuff like that, which basically are small compared to the other guys. We can start to think about what is the net radiation coming in and going out at the top of the atmosphere, okay? Because we should be able to write an equation for the fluxes at the top of the atmosphere and the fluxes at the bottom of the atmosphere. So that's albedo. Okay, so we can kind of think about this, that we basically want to think about adding up. Okay, adding up these terms up here, these terms here, okay, and then a separate equation that basically balances the fluxes at the Earth's surface. Okay, so at the top of the atmosphere, okay, we've got our solar flux coming in, okay, and we've got minus the amount that's being reflected back out. So that's what this part of the equation means over here. And then we've got this term here, which is the amount of radiation that's emitted by the surface minus that that's been absorbed in the atmosphere. Okay, that's this term here. Okay, and then we've got the amount of radiation that's being emitted out to space from the atmosphere having a temperature. Okay, and we can do the same thing for the bottom of the atmosphere. So the bottom of these fluxes down here. So importantly now, just like before, we've got a series of equations that we can think about trying to solve for the surface temperature of the Earth. So in this case, we've got two equations, okay? And if you look at those two equations, we've got, we know the solar flux, okay? We can make a good estimate of the albedo, okay? So if we know what this term is, the emissivity, or we can assume that the emissivity and the absorptivity are the same, okay, we have two things that we don't know. Okay, we don't know the temperature of the Earth's surface, and we don't know the temperature of the atmosphere. Okay, but fortunately we have another equation that has those two unknowns in it. So we have two equations, we have two unknowns, so that means that we should be able to solve that equation to find out those things. Okay, and you can go through this in your own time if you wish to. Actually, I strongly recommend that you do, because if you can do this, you kind of understand where this equation comes from. Okay, so this we can combine those two equations at the top, and this gives us an equation that gives us the surface temperature of the Earth And then we've got a similar equation to we had before, except we've now got this term at the bottom that has emissivity in it. So how, or absorptivity, which is basically how transparent the atmosphere is to long-wave radiation. Okay? So this is basically the greenhouse gas effect, this little e at the bottom. Okay, and you can also kind of do some more maths, and this is on the Learn Site PowerPoint thingy, so you can look at that. That gives you a relationship between things like the temperature of the atmosphere and the temperature of the surface. So you can work that out as well. Okay, so you can basically do all that, and you can get a relationship between the surface temperature of the Earth and also this term we had before, the TE, which was basically the Earth without any atmosphere. So, and we can also get this relationship between the temperature of the atmosphere and the temperature of the Earth's surface. So it turns out that the ratio of the atmospheric temperature to the Earth's surface temperature is kind of fixed in this model. Okay, so if the atmosphere heats up, the surface of the Earth will also heat up. Okay, we can't separate those two. Okay, and if we plug numbers into that, which we kind of like with some parameters we kind of like estimate from measurements of the shininess of the planet, and we can basically estimate how absorptive the atmosphere is. So the atmosphere is about 0.8, so about 0.8 of the long-wave radiation actually gets trapped in the atmosphere, and only 0.2 gets out into space. We can plug those numbers into that equation, which is something that you should also do in your own time. You get a temperature that's much warmer than the previous model. Okay, so that's good, right? So we're getting something that's much more close to the actual surface temperature of the Earth. Okay, so we've got a model that we can now use to try and explore what might have changed in the past. Okay, to change the temperature of the Earth and determine how habitable the planet was. Okay, so I guess just to summarise, so we've got three equations. The first one describes the surface temperature, the second one describes the atmospheric temperature, and this third one, which was the one I went through in the video, and that describes this thing called emission temperature. Okay, and this is a term that's actually used quite a lot in planetary sciences, because this is the temperature of any planet if it didn't have an atmosphere. All you need to know is how shiny that planet is, the albedo, and how far away it is from its sun. Okay, and how bright the sun is. It's also relevant to the Earth because this is the effective temperature of the top of the atmosphere. So if you were in space and you were looking down at the Earth and you were trying to basically work out what the temperature of the Earth is just from the radiation that's being emitted from the planet, okay, you could use this equation, because if you're just looking down the Earth, maybe from a long way away, you might not know if the Earth has an atmosphere or not. All you can see is the radiation coming off that planet. Okay, so this is called the planetary emission temperature. Okay, so it's effectively the temperature of the top of the atmosphere. It's basically the temperature that space thinks the Earth is. Okay, because the Earth is actually emitting the long-wave radiation from the Earth's surface. It's emitting radiation from the atmosphere. Okay, and it's also giving off the radiation that's just bounced off the surface from the sun. So those three terms kind of add together to give this emission temperature, or this emission radiation, which basically results in this emission temperature. Okay, so the things to think about. So you should know what all the terms in these equations are. So S0 is the solar flux. So that's in units of watts per meter squared. Okay, so W m to the minus 2. The albedo is the reflectivity of the planet, so what fraction of the incoming shortwave radiation is reflected off. And that doesn't have any units because it's a fraction. Similarly, the emissivity or the absorptivity, okay, E, that's some weird Greek E, I can't remember the actual name, I think it's eta. Anyway, doesn't matter. Squiggly E. That doesn't have any units. That's just the fraction of radiation that's absorbed by the atmosphere, or the fraction of the black body radiation which is emitted from the atmosphere. And then at the bottom here you've got this Greek sigma, which is kind of like a an O with kind of like a quiff on the top of it. And that's the Stefan-Boltzmann constant, which is 5 points something else times 10 to the minus 8 watts per meter squared per Kelvin. Okay, and that per Kelvin is important because it means that these temperatures, okay, are all in degrees Kelvin, not degrees Celsius or other crazy units. Okay, so we've constructed a model. Okay, so we can now look at what might be how we can use that model to tell us something about the planet. So these are two graphs through almost all of geological time. So we go from the present at the top down to kind of almost 5 billion years in the past. Okay, so when the kind of solar system is kind of first forming. And one of the things about the solar system and the sun in particular is that through time, the sun has been getting brighter and brighter and brighter. Okay, and that's as more nuclear reactions carry on in the sun, more heavy elements are formed, more helium, more lithium, and that makes the sun denser. Okay, that increases the pressure in the sun, which increases the efficiency of all of the nuclear reactions that are happening on in there, and that makes those reactions more efficient, makes them hotter. Okay, so through time, the sun has been getting hotter and hotter and hotter and hotter. Okay, so if we look at our equation, look at our equation now, up here. So that's basically this term here, the solar flux through time, must have been lower in the past. Okay, so we can just look qualitatively at this expression up here and see the solar flux is on the top of this kind of fraction here, which means if this term gets smaller, this term gets smaller. Okay, and we can see that in the past, if we didn't have any greenhouse gases, the Earth's temperature would be much, much colder, okay, than it is at the present. Okay, so that kind of statement makes a bunch of assumptions that the planetary albedo hasn't changed in the past. Okay, you might think, well, maybe billions of years ago the planet wasn't as shiny as it is now. So if actually we made the planet darker, okay, and you might want to think, could the planet have been darker in the past? Well, we wouldn't have had any trees, so maybe the continents might have actually been more desert-like and more shiny, but there might have been more ocean. Okay, more ocean in the past, smaller continents. That would make, because the ocean is dark, make our planet darker. So we might think about tweaking around with some of those parameters to see if it's possible that we could, in fact, keep the planet habitable, okay, during these times down here when it should be really, really cold. Okay, it turns out that if we make this term here big, okay, so if you make the atmosphere more absorptive, if we add more greenhouse gases to the atmosphere, because this is on the bottom but it's minus, so this makes this term, if we make this term bigger, this term gets smaller, which makes the whole bottom thing here smaller. So if we have more greenhouse gases, the temperature will go up. Okay, so this is kind of another kind of like run of the model, okay, which predicts if we have a little bit more greenhouse gases, we can start to make the average temperature of the Earth kind of more habitable through geological history. Okay, so one of the things that has happened through geological history that we know is that the planet has been habitable. Okay, so life has managed to kind of like trundle along and kind of evolve and stuff, which you probably went through with Steve in great, interesting detail. So what has happened is that these parameters in this equation at the top have changed through geological time, and the temperature of the planet has basically stayed in this kind of habitable range where liquid water has been available at the Earth's surface at all times. Okay?